Let us look at another numerical problem. It is a surface emits as a black body at 1500 Kelvin. What is the rate per unit area in watt per meter square at which it emits radiations over all directions corresponding to theta varying between 0 degree to 60 degree and over the wavelength interval 2 microns to 4 microns. So basically here we are given with the wavelength range varying between 2 micron and 4 micron, whereas the value of theta is equal to varying between 0 to 60 degree. So in this range, we have to calculate what is the total amount of the emission for a black body. You should remember that a black body is a diffuse surface, means its intensity of radiation in all directions is same. So the solution is the temperature of the surface that emits as a black body. This is the first thing that we know. To find is rate of emission per unit area over all directions between theta equal to 0 degree Celsius and 60 degree Celsius. And the wavelength range is between 2 microns and 4 microns meter. So you can see here, this is the black body which is shown here as at 1500 Kelvin. And you can see this is the cone actually. This cone. So we have to calculate this solid angle and how much is the radiation leaving in this particular range actually of theta varying between 0 to 60. So if I take theta at this particular location, the value of theta is 0, whereas if I go up to this particular point, the value of theta is equal to 60 degree. So the assumption is surface emits as a black body. So it's not a assumption. We also we have already been given this in the question in the first line itself. Now here one important thing is that this equation should be known to us, that emission, total emission will be equal to I lambda E, which is a function of lambda, theta and phi, cos theta, sin theta, d theta, d phi into d lambda. And this equation shows that the energy is emitted in the whole range of the wavelength, which is shown here from theta to phi, theta to alpha, theta to infinity. And here this is the angle phi from 0 to 2 pi, and this is the angle theta from 0 to pi by 2. So this value gives us the emission from a particular surface in the total theta direction as well as the phi direction. Now here we are given with a particular value of the theta, and phi is 2 pi, or from varying between 0 to 2 pi actually. So what we can do is we now have to calculate the value of delta E. Why delta E? Because in the equation it is given E. E means the total radiation which is going in the all directions and all wavelength range actually. But here we have a limited range of the wavelength and a limited range of the value of theta actually, whereas the value of phi is varying between 0 to 2 pi. So another thing is that here we are taking I lambda A. So it is for a particular surface which is not black, but here the surface which is given to us is the black surface. So I can replace this I lambda E by I lambda B, because B here stands for the black surface. The remaining equation remains the same: cos theta, sin theta, d phi, d lambda. And what we have to do, we have to take the wavelength range lambda varying between 2 microns to 4 microns. Then phi is varying between 0 to 2 pi, whereas theta is varying between 0 to pi by 3. Pi by 3 means 60 degrees Celsius, 60 degree actually. Now what I can do is I lambda B. Now this I lambda B is basically independent of direction actually. It is because it is diffuse. So whether it is any direction, you talk about any theta value, the intensity of the radiation for emitted by the black body will be same. So this can be taken out of the integration sign, means it is not dependent on either theta or phi. So we can take it out of the integration sign and we can keep it here. So I lambda B, and here this is the value of phi varying between 0 to 2 pi, and this is theta 0 to pi by 3, and this is the equation. And here you can see this is d lambda. So what we have to do, first of all, we can integrate this equation with respect to d phi, and these are the limits, so we can get this value as 2 pi, and then this value of sine theta cos theta can be written as, this sine theta cos theta can be written as sine square theta by 2 after the integration actually. Okay, so and the limits are between 0 to pi by 3, and here we still have the value of d lambda, because we have not integrated this equation with respect to lambda yet. So you can see it here, we this cancels out, we are left with pi, and you can see here, and 0.75 actually comes from this value of the sine square theta. Okay, when we put the value of sine square theta corresponding to pi by 3, means it's sine square 60 and minus sine 0, so then we will get this particular value of 0.75, and inside the integral for lambda between 2 to 4, this is the equation, and you must remember that this value in case of a black body is equal to EB lambda. So what I can do next is that I can write this equation as 0.75. Okay, I can multiply here by EB, and here it is EB lambda d lambda divided by EB. So it is varying between 2 to 4, but this EB is the total value of the integration. So rather see this once again, I will just change this equation a little bit so that there is no, so I can say that this value is, integration is from here to here only, 2 to 4. So basically if you see, then this value, this whole value is basically the fraction of energy which is lying between, I can write it as 0.75 EB, and this will be equal to fraction from 0 to 2 micron, 0 to 4 micron minus fraction 0 to 2 micron, and that is how we can calculate this value. So you can see it here, this is given here. So you can see it, whether we take it in integration or not, that will not affect. So this value I am talking about, this whole value, that will be equal to fraction from 0 to 4 and 0 to 2, and we have to calculate this value of fraction of energy by this value of lambda t. So lambda 1 t is 2 micron meter into 1500 Kelvin, so that will be 3000 micron meter Kelvin, and this value can be seen from the table 12.1 which is shown here. It is 3000 lambda t, so this is the value of lambda t which is 3000, and this is the value of f0 to 2 which is the fraction of energy in this particular wavelength range. Then we have calculated 4 into 1500, so it comes out to be 6000, and corresponding to that we have the value 0.737818. So we have taken here 0.738 after rounding off it, and then we are left with 0.75, 0.738 minus 0.273 EB. So this gives us this value, and we know EB is given by sigma t raised to power 4. So from equation 12.6, 12.6 is nothing but this equation only, and I can put this value 0.75, 0.465, sigma value is 5.67 into 10 raised to power minus 8, which is the Stephen Boltzmann's constant, multiplied by 1500 Kelvin raised to power 4, and the value comes out to be 10 raised to power 5 watt per meter square. So now let us try to understand this result actually. Now you can see this particular value, 0.75. When does it comes into picture? This comes into picture because of the directional cause actually, because the radiation is in a particular direction. So it says that the total hemispherical emissive power is reduced by 25% due to directional restriction, because we are talking about a particular direction, that is theta is varying between 0 to 60. So this 0.75 came from that. Otherwise, if we would have considered theta to vary between 0 to 90, this value would have been 1 actually. So it has been reduced by 25%. Similarly, when we are calculating this value of fraction, it is 0.465, and this is because we are taking a particular range only of the emission between 2 micron meter to 4 micron meter, and because of that you can see the emissive power is reduced by a factor of 53.5%. So, and it is the spectral restriction, that is lambda is varying between 2 to 4 micrometer. So, this is how we can calculate the value of emissive power of a black body in a particular direction, in a particular range of the direction, as well as in a particular range of the uh, um, wavelength.